Okay, and for those of you who've joined us at 2 o'clock here, welcome back. For those of you that have just signed on, I want to welcome you to this special Design World webinar. You're here for the webinar entitled Endless Possibilities, Understanding the Expanding World of Machine Springs. And I'm the moderator for today, Miles Budimir. I'm a senior editor here at Design World magazine. A couple of things, a couple of points here just before we get started. This webinar will be available afterwards at designworldonline.com and also through email. So everybody who's registered for this webinar will get a copy of the webinar, but they will also get a copy of a special white paper, which will also be going out as well to everyone who's registered. Also like to remind everyone that we're going to have a Q&A session at the end of this presentation. So at any time during the webinar, if you think of a question, if something pops into your head, just feel free there to post your question on the question tab, and we will do our best to get to everybody. Sometimes we don't, but most of the time I think we manage to get to everyone. So, and finally, if you would like to, if you're on Twitter, if you'd like to tweet about this webinar, the hashtag for the webinar is hashtag DWWebinar. So feel free to do that as well. So as I've already mentioned, I'm the moderator, Miles Budimir. I'm a senior editor here at Design World, cover mostly motion control. And our presenter today is Gary Beam from Helical. And let me tell you a little bit about Gary's background. Gary graduated from Cal Poly Pomona with a bachelor's degree in mechanical engineering. And several years later, he went to Cal Poly at San Luis Obispo, where he obtained a master's degree in mechanical engineering. He's done some very interesting work over his career. He's been with Helical for almost 40 years now. And included in this period, he's focused on developing closed-form FEA techniques to understand and predict the behavior of single-start and multiple-start flexures configured from a helix. He's also done, or Helical, I guess, and Gary have done some interesting work as well with the space station, with the shuttle program, and as well, even more recently, with the Mars rover. So those are some of the more very interesting applications that that Gary and Helical have worked on. So he brings a wealth of knowledge to this area, and I'm glad that we have him with us here today for this special webinar. And I think with that, I think I'm going to hand it over to the expert, which is Gary Beam, and he will take us from there. Gary, I think it's all yours.
Well, greetings. Thank you, Miles. This is Gary Beam, and the company name here is Helical Products Company. We get so used to calling it Helical that we forget that the other words actually do exist. You have on the screen the title that we're going to be using today, Understanding the Expanding World of Machine Springs. This is actually a second webinar on this subject, and what I'm going to present here is some of the things we had in the first one and then some additional things. It's kind of a hybrid presentation, just so we can be a little bit trendy, of course. And we'll just push on through here. This webinar is, we're coming for another slide, and there we go. We got it figured out. The presentation is really based in a paper that I wrote and have been rewriting and re-editing through the years. But basically, it's a comparison of machine springs and wire-wound springs. And so the machine spring world is a huge world. Or, excuse me, the wire-wound spring is a huge world. There's probably thousands and thousands of manufacturers. In machine spring, there's one basic manufacturer. So we're kind of the small insect on the big tree. But we're hoping to make a little noise and give you some reasons today to see why that noise exists. Basically, if you have an application where you need elasticity, you need to make a decision whether you want to use a wire spring or a machine spring. and both are valid solutions to most problems. So here's a picture of couplings that have been made at Helical Products. The company has been founded in 1958, which is precedes me, as you can tell if you've done the math. And you can see that we did migrate into the machine spring world because couplings and machine springs are basically the same thing but used slightly differently. Okay. So here's some pictures of springs that you've all seen and used, and I've seen and used too. I started my professional career even in school designing things with wire wound springs, and there's so much to choose from. But you can tell the difference between a machine spring and a wire wound spring, and let's see if we can get a picture of that. Here's some machine springs, and basically the flexures look a lot similar, although the coils are rectangular and square in section, but there's also the addition of attachments. Here we have a wire wound spring, which is typical of a closed and ground wire spring. And we have a machine spring, which is pretty typical of a similar machine spring. And then there's a second one, and we'll talk about that second one in just a minute. But these wire springs have been around for a long, long time. I was out on an island in Lake Erie, and I found a wire wound spring from the American Revolution, and out there, and that wasn't the first time these things have been used. So they've been around for a long time, and they've been very successful in helping all of us do and manage elasticity. The two springs on the left, one wire and one machined, are both single started springs. But the one on the right, and you can see there's more coils there, is a double started machine spring. All three springs have the same rate, and all three springs were manufactured with modern CNC controlled machines. So there's a lot of similarity in these products, but there are some subtle differences. This is a topic that was pretty interesting in the first presentation. People wanted to know about the precision of machine springs versus that of wire. Both manufacturers can easily do 10% precision springs. There is a difference, though, for the machine spring folks and the wire spring folks. Often the way wire wound folks can get high precision is by sorting springs. If we had to sort springs at Helical, we would go out of business because the machine springs are a little bit more expensive. And we're going to talk about that in just a little bit. But 10% is common from both sources. 1% is probably available from the wire folks. You'll have to work at it a little bit, but you can get it if you need to. And with machine springs, we manufacture a number of things at the 1% level. At 1/10 of a percent, I'm speaking for the wire folks here. I suspect that they probably don't want to perform that, but maybe at some time we can get somebody on here from a wire company and they can talk about that. I assume that they can't do it at this point, and the machine springs are a maybe. We have manufactured and shipped springs at that precision level. The size, we skipped no we didn't. Materials that springs can be made out of are numerous. The wire people have a whole set of special wires that get used, and they're very successful with that. The machine springs, on the other hand, stay pretty much with materials that get their strength not from cold working and not from quenching, but rather from an aging. And that aging is usually around 900 degrees, whereas those other activities sometimes will be higher than 900 degrees. And I've added to this list X750 Inconel, as you can see in that first corrosion-resistant steel list. A lot of the space people, a lot of the medical people like the X750 Inconel. The other spring wire that's really interesting is this C300. That's a Mar aging stainless steel that has a strength of about 300 KSI yield. The other non-ferrous materials available in machine springs are the high-strength aluminums, the 38644 beta C titanium, very high strength, very corrosion resistant, and then some non-metal surfaces, non-metal materials, Delrin and Ultim. In fact, these I've seen some Ultim springs being machined out in our shop just prior to this presentation. Okay. Regarding sizes, that's a dime. I don't know how good your picture is, but that little round spot is a dime, and above it is about one of the largest machine springs made. So you get a sense for how big these things can be. But you've also seen wire springs that would not even fit in that picture. So we're limited a little bit to size with the machine spring, and that's on the big side. And on the small side, what you see on the right is about as small as we can make. Wire springs, you know, can be smaller because they're limited by the size of the wire, and we know that wire can be pulled down to you know, tens and 12 thousandths diameters, maybe even smaller, and they can be formed. So the machine springs are really a subset of the size capability of the wire springs at this point. Now let's take a look at some of these machine springs. There we go. And basically, the feature here that is really important is are the attachments. And these springs here are predominantly either extension springs or compression springs. And you can kind of look at the group and see which ones are which. The compression springs will have bosses on the ends or threads or something so you can get a hold of it. And the pure compression springs, or just compression springs, do not need any special attachments. So there's, as you look around there, you can see those two cases. Let's talk a little bit about the coil sizes and the slot sizes. Yeah, as we come down through the selection in coils, we can see that for round coils, obviously the wire springs are available, and they are not available in machine springs. At least they aren't available yet. Square wire is also available to the wire folks and available to machine springs because that's the typical cross section of the coil. there's a rectangular in the radial. If you'll remember back at that one of the first slides where you saw couplings, all of those coils were very radially rectangular. And you can do that with wire to a limit, and people have been quite successful with it. And so it isn't until you get to the really high ratio radial does the wire start dropping away. And I think probably those examples you got in those couplings would probably be the nose here for the wire people. And with machine springs, they're still available. Also, you can be rectangular in a longitudinal sense, and that's kind of bent flat stock. And anything that can be bent, the wire folks are really good at that. Helical can also machine it in those shapes, and in both high ratio and low ratio. When we look at the slots, the zero width slot is a real interesting slot for the wire folks, and they are. I've seen a lot and used a lot of those, and they're typically extension springs when they have the zero width. Machine springs can have a zero width with some special heat processing after it's been made. But the wire people have a unique item, and that's where they have a zero width with a pre-stress. The classic screen door spring is one of those, and they're readily available, and that's a real useful extension spring, and not available from a machine spring perspective. As far as slot widths, 100 thousandths of an inch is readily available in both. But when the slot widths get very large, a quarter of an inch or wider, it's only a maybe that they can be made in machine springs. Because remember, we are removing material, and at some point, removing the material at a very high helix angle is problematic. The number of coils, small number of coils, one coil, is readily available for both wire and machine. 20 coils is the same. 50 coils is starting to stretch the machine folks. But as far as wire is concerned, you can have as many coils as you've got wire in your feeder. Garter springs and so on have lots of coils on them, and they're really useful. But machine springs, we've made 50 coil items, but they're a pretty rare item. Okay. Yeah, we're a little slow here on the transitions, but here it goes. It's a computer issue, right? In any case, since the wire springs can have such wide slots, you'll find that they can be compressed to a larger percentage of their free length. Whereas with the machine springs, well, about 40% of the free length is normal. We can stretch it to maybe 50% under some circumstances, and I think that 60% that's written there with the small maybe means just that. The moon and the sun have to be aligned, and a few stars too. So, of course, 90% is, well, with a conical spring, which is not something we've talked about here, but with a conical spring, the wire folks can go ahead and make that spring just fold right into itself and get right down to one coil width, which is pretty neat. Okay. There there's the header here says equivalent machine springs must be longer, and let's address that a little bit. Here's a typically ground, closed and ground wire spring, and you can see the active coils go all the way to the very end. And there is the potential of storing energy in that coil all the way to the very end of the coil. And this works out very well for automotive valve springs. It keeps the whole package as small as possible. And also other applications where length of the overall spring is a sensitive issue. In the machine spring, we have a little different issue here. The slot ends before the end of the coil, or end of the spring. And so that whole end of the slot will not close, although we do store energy all the way to the end of the coil. That the slot will not close, and of course the structural member that's beyond the slot cannot be compressed. So for trying to get the same performance in the same OD and ID, and maybe even the same number of coils, a machine spring will have to be longer. So that means if somebody's trying to pull wire wound springs out of an assembly and put machine springs in right behind it, there's going to be a compromise of some sort. Okay. Let's talk about money here. We all like to talk about that, don't we? The cost-wise is that the wire wound springs benefit significantly from fast production. Even though both systems use CNC systems, one is removing material and the other one's simply bending it. So the fact that material is being removed takes a lot of time. And I know I've bought wire wound springs for the things I like to do at home and so on, and I've spent less than $1 for them. And I don't think that's going to happen with a machine spring, even at very high quantities. So basically, you need to ask some questions. If you are considering using a machine spring, some of the advantages you need to be using and getting from them are in this list right here. Integrated attachments. We've seen some of those and can get an idea of what they can do for you. There's a chance for some enhanced performance. And that would be a little bit more linearity because that wire spring lays down on itself a little bit, and so it'll change a little bit more. Also, we jump to the bottom, when those two ends come together at the extreme compression, there's the potential of either sound or there's the potential of a little bit of debris being generated. So in those environments, medical in particular, where no debris is allowed, no one wants metal flakes in their body, the machine spring is a real plus because, again, the coils, if used properly, the coils will never touch. Also, we go back up the list again, we'll see a word called multiple starts. And this is this is an aspect of machine springs that's a real plus, and we'll come to that in just a minute or two. But this is an area that the wire folks don't participate in, and the machine springs can. Also, we've talked about precision and down to their reduced assembly and acquisition efforts. From a value engineering standpoint, some old terms, you can integrate a number of different parts into the machine spring if that has value. And so while you're paying a lot more money for the machine spring, the fact that you're able to bring multiple parts, pieces together into one, that will have a potential benefit. It will help offset the extreme difference in cost. Okay. Improvement of metal. I think we can skip the fancy words there and just say, can you peen machine springs? And wire springs can be peened, and I've used them, and so has many people. And one of the reasons they can be peened is they have these wide slots on them, and the shot can go through and catch the ID of the spring. And while peening does do things like change the length of the spring and a few other things, it still does help the spring metal, and that's a good thing. With machine springs, it's almost always the case that the slots are too narrow for a shot to go through to be beneficial. And so if you did put shot against it, it would be impacting just the outer coils, and boy, would the coils get longer at that point. So the metals that are chosen for machine springs are typically high strength, fatigue resistant materials, and those materials are what contribute to the long lives of high performance springs. So again, virtually no peening is really available for most things. Now, there can be peening of parts of the springs if some targeting is necessary, and I've seen that either in the attachments or at the very end of a coil. It's a possibility, but not done very often. In another area, it's a common thing to see wire springs that have either zinc or nickel protection on them, corrosion protection, and that's a good thing. Plating of machine springs is uncommon, actually, because we have all those sharp edges, and we do know the plating, since there's a charge that's associated in the bath, that it does not, it's not usually a benefit to machine springs. Okay. The machine springs that are made from aluminum, though, are anodized, and that is, of course, a corrosion preventive device. Also, machine springs can be coated. There are some coatings that are very good for that, but it presents a little bit of problems in the sense that how you interface with the spring and where the coating is and so on, and so there may be some masking requirements to make sure that is as good as it goes. Okay. Now here's some interesting pictures. We know that wire springs and machine springs do wind and unwind when they're stretched or compressed, and sometimes that activity is not desired. So both in wire springs, this what looks like a coupling here in the foreground, that's a right and left-handed flexure. And that flexure, the center section actually moves. It tends to move one way or the other way, depending on whether the spring is being stretched or compressed. And the ends don't twist at all. And so that's one way of solving this problem. There's another spring just to the right of that, the smallest one in the picture, and that is another example of that same idea. It just happens to be that this happens to be a double-started spring. And we're going to talk about multiple starts in just a few minutes. But if we go up to the spring in the background, you'll see that there's two springs there. And what we've done is we have a right-handed spring, right-hand wound spring, and a left-handed wound spring. And the design is such that the reaction torque is equal and opposite. And so one can then benefit from no rotation in this package. And again, that is a double-started spring. So you get the benefits of the double start and no rotation. That's a pretty sophisticated spring pack right there. That was to be used in instrumentation of one sort or another. Okay. Now, on the subject of multiple starts, here's what they really look like if you were to cut them open. You can see the single start on the left and the double start on the right and the triple start in the back. From a cost standpoint, it's make the spring once, make the spring twice, or make the spring 3 times. So it does have some costs associated, but it does things that you can't really get with a single start. And we have in this next slide a picture of what happens with a single started spring. The force comes into it as a force, and that could be a wire wound spring on the left there, or it could be a machine spring. But it comes in, and that force comes in, and it stays there. But the line of activity is down through the center line. So you end up with a force at a distance, and all of us technical people know that's called a moment. And somehow that moment has to be resolved. And you can do it, and it can be just fine. There are times when those moments can be attached. It can be resolved by attachments or in seating devices that are used for both wire and machine springs. But they're there, and they can be also a problem. In a double-started, multiple-started spring on the right, you can see those two forces, but the distances are opposite, and that makes the resulting moment different, and the moments resolve inside the spring to 0. And so if you put a pure force on the end of it, and if you want to put the force on a spherical surface, it will not tip. It will not try to slide one way or the other way. It'll just stay there and take the force. And we can also do this with a triple started spring. And we have some videos of springs in this sense. In the next slide there, if you go to our website, which would be heli-cal.com, and you can put www in front of it or not, if you want to or not. On our website, you can choose this link, and it's on the first page. It comes up, so it's easy to get there. And there are videos on YouTube, and they will show you what happens when you take a spring and you put a spherical device on the top of it, basically a ball bearing in a cup, and you press on it. And oddly enough, not oddly enough, but you'd expect it, a single-started wire spring acts the same as a single-started machine spring. They both tip, and the moment when it becomes large enough causes the spring to roll one way or another due to that ball bearing. And it's a real graphic explanation of the topic that we just talked about. But it also has videos regarding torsion springs. It's something we're going to talk about in just a minute. But the torsion springs video is good in the sense because there is a moment issue with torsional springs and in regards to tangs. When you put when you have a wire spring and a tang and you put a force in that tang, you get a moment. You get the force, you get the reaction that you want, but you also have a moment or a translating force, I guess, that you have to account for. And there's an example of what that is too. So when you get a chance, take a look at these YouTube videos and so you can better understand what I'm talking about. Okay, let's go on to torsional springs since we brought that up. Here's a whole group of torsional springs, and of course these are all machine torsional springs, but some of them have some features on them that are common to wire springs. If you look here, you'll see one with tangs on it, and those happens to be longitudinal tangs. Are coming out the end of its spring, but these tangs can also go radially out the side, and this is typical for wire torsional springs, and we've all used, maybe even designed with torsional wire springs. But whenever we've done that, we've had to do something to resolve that force that's out there. And also we've had to worry a little bit about what happens when you bend that wire from its straight condition to a hard right angle bend, whether it be coming out the end longitudinally or going out radially. What happens to the section of the spring in that area, and do we have a stress there that's possibly not beneficial to the life of the spring? Well, with machine springs, we can put features on the ends of these springs. We can put features such as the tangs that you see there, but we can also make those tangs thick and robust. And if we only had one tang, we could make it thick and robust. But we can also put slots in these things, and there's ones with slots. That one with slots is interesting. You might want to take a note of it. That's made out of 38644 beta C, and because beta C is a special alloy that has a body-centered cubic structure, it doesn't creep under load, and that spring sits at about 85%, maybe even 90% of yield for years before it gets used. So that's kind of an interesting machine spring. But the others there have all kinds of other ways of getting hold of torsional springs. We've got gears, splines. There's holes in the ends of these springs. The big spring on your right is a typical aircraft torsional spring. You can see the small holes. That's used to hold the spring in place, and the torque is applied then by the two holes that are 180 degrees from each other. In aircraft work, again, there's a spring just to the left of that one, and it has splines, and that spring is an interesting device. That is a mechanical fuse for protecting the fuel system in a jet engine. What happens in what happens in these engines is that they can't fail. If a fuel system were to fail, the engine would lock up, and of course we don't want engines to lock up because they're turning 18, 20, 30,000 RPM, and that usually removes them from the wing of the airplane. So this was designed to allow a failure, and there's a neck down section. If we can get the, right up there, there's a neck down section there with a reduced section where the failure is there. But we also know that in all gear systems, even these wonderful jet engines we have, there's a little bit of harmonic because nothing is as perfect can be, and so there's a little bit of torsional hunting in the system, and that was prematurely breaking that fuse. And what's done is a triple start flexure was put in that torsional spring to take out that increase and decrease and increase and decrease in torque going across the shear section. So that's been a very successful design. In any case, torsional springs, and their strong point again is in the attachments. I'll try not to get you tang dizzy here, but the tang word is used quite a bit. The attachment types, wires have the radial tangs, both they go internally and externally. Machine springs can do the same thing. And when you do that, you have to, as you can see with the asterisk that's there, you have to figure out somehow to resolve the resulting force, whether it's a machine spring or a wire spring. You can have dual tangs on machine springs. In other words, tangs coming out both sides or going in towards the center. On the machine spring, you can't do that on a wire spring because the wire ends only in one spot. As far as axial springs, you can have tangs also, but they also have the issue of force resolution. Dual tangs, both internal and external, are available on machine springs, but not on wire because, again, it's one piece of wire. There's pinholes we saw earlier. There's also geometric shapes such as squares and hexes. I've even seen ellipses, shafts with keys. There's all kinds of ways to resolve or apply moments to torsional machine springs. Okay. This picture that's on the right is one that probably everybody recognizes. Everybody who's been through some formal vibrations training. And it's a single degree freedom system with a mass and a spring. And when we saw these, we just assumed that, yep, there's the mass, there's the spring, and yep, it's a single degree of freedom system, so it made it easier to analyze, and away we went. Little did we know that spring didn't exist, at least when these first diagrams were made. A wire-wound single-started spring, which is typical wire-wound, and a wire-wound even machine spring will not work in that system. There will be that moment that I was talking about earlier in existence there. And so to make this thing work, somehow that spring has to not have a moment as a result of deformation, and the forces need to be in line and always in line. And the springs that work for that the best are double-started machine springs and triple-started machine springs. The reason you would want to triple start is that double-started springs are, in a lateral sense, different in their stiffness, both in translation and in bending, on orthogonal axes. So when you're in line with the ends of the springs, it'll be one stiffness, and if you're 90 degrees away from the ends of the springs, there'll be a little different stiffness. And that can cause trouble in a dynamic system or in a resonant system. So the gold standard right now is the triple-started machine spring, because it is uniform in stiffness, both in translation and in bending, in all directions. And this is a good use, a very good use of the multiple started machine springs. Well, here's some pictures of machine springs from years past. You can see one trying to climb out of the picture there at the top. But size-wise, the little dots that we see in the middle are the small ones that we saw, and that tall one is the long one that we saw, also showing the sizes of springs. But what you can do with these things as far as attachments and what you can do with different ideas. The one there that has the big oval, you see there's two flexures, right and left hand flexure there. That was one used in a satellite, and that oval was used to get the wires out. So the wires came up the middle and came out there. And there's flat springs, and there's springs with all kinds of different features. I even see one with some radial tangs over here. So that's what we just talked about. So in any case, this is what's available with machine springs, and this is a little bit of how they compare with wire springs. Let me thank you for sharing this time with Helical and myself, and we'll go back to our heroes at Design World and maybe have some questions.
All right. Well, thanks, Gary. This is Miles again here. Thanks very much for that great presentation and some very useful and informative things there. So as I've said here before, and I want to remind our audience here, we're open up to a Q&A session now. So if you have any questions there, feel free to post them, and we will try, in the remaining few minutes that we have here, we'll try to get to as many of those questions as we can. So let's see what we've got here in terms of questions. Try to get to as many of these as I can. Here's a question from Paul, and he wants to know if you've done any springs out of graphite.
Golly, Paul, the answer is affirmatively no. I've done them out of we've done them out of some interesting plastics, and I can remember having one done. It was one about two inches long, and I had it in the palm of my hand, and I was carrying it like a delicate object across our shop, and by the time I got to the far end, it was broken. And I have a feeling that the graphite is going to be the same issue. the other issue that people talk about, and it hasn't happened yet in the wire spring world. It might be in the machine spring world. It might be existing in the wire spring world. Is that if you have fibers in your material, whether it be plastic or carbon, you have to make sure that any machining activity that you do, it doesn't cut across a fiber, because a fiber that's been cut is one that is a location where there's a potential failure of the spring. So it's been an interesting issue, but the wire people may have made some of these things, so you might want to look at them for that.
Okay. All right. We have another question here, and let's see. Here's from someone named RK, and the question is, can you make my part flexible? And I'm not sure. Maybe that'll be clear to you. I'm not sure if it's talking about probably not the spring, but
yeah. Well, let's. It's not uncommon for a manufacturer of goods to be able to make a spring blank on their own.
Mm-hmm.
Okay? So we can integrate a flexure into their assembly. So they might have an involved assembly, and one segment would be where they need some elasticity. We can add that to their assembly and make machine springs that way. Or if the manufacturer is one that if they wanted to spend their money in their own plant, which is not a bad idea from a management standpoint, and just provide the blanks to Helical and have us put the flexure in the blank, we can do that too. And we call both of those systems generate only, and the process that we use to create the flexure is called generation. Mm-hmm. So yes, I think we can service those people well. In fact, today we're producing parts of that nature in our shop.
Okay.
And again, these are parts that the manufacturer has sent in. They look like springs, but they make their own blank, and we put the flexure in their blank.
Mm-hmm.
Okay.
Okay. There's another question asking about, is there a catalog, which kind of had me thinking too when you showed that last photo on that last slide. There was one of my questions, maybe that kind of goes parallel with that question, is how much of your maybe of your business really is maybe, let's say, kind of off-the-shelf springs versus something like custom springs, right? Where someone would come to you and say, can you work with me to basically make a part flexible, right? So
yeah, good question. It's an easy one to answer.
Okay.
Because we do not have a catalog of springs.
Okay.
And so all the springs that we have done are built for a specific application.
Okay.
And we've designed. We're getting close to 30,000 different flexures. So you can see we've been busy at this. But as far as a catalog spring, we're working on what's called a calibration spring, and if we can get, once that comes out, there will be a catalog spring, and and so that will allow people to have a building point. But in the meantime, we keep track of what springs we do make, and people, when they come in, we look through what we've made so far and see if we've already solved that particular problem. Or application, and then we go forward with that. We also provide free engineering, so people can call us and talk to our engineers, and it's easy to get a handle on whether what's wanted can be done, and so we're easy to get along with in that sense.
Okay. All right. There's a bit of a more technical question, I guess, but the question comes from Mark, and his question is, what are the differences in rate and stress calculations relative to wire-wound springs?
Well, okay. I came into this world of machine springs trying to solve that exact problem, fresh out of grad school, and I found that there was really no system to be able to evaluate machine springs thoroughly. So we at Helical use FEA. We use very explicit FEA systems that we've put together that work, and we're happy to share those results with customers. But as far as machine springs are concerned, we use no Timoshinkles work, walls work. They'll get you sometimes in the ballpark, but sometimes not. And you don't know which one you're in until you make the part and find it does or doesn't work. So we use FEA.
Okay. All right. Let's see. I don't know if we have time enough for maybe one more question. We're running up to close to 3 o'clock here, but maybe just one more question here. Here's one question from Daniel. He's asking about if you can tailor a spring to have spring rates that vary with compression. Is that a possibility?
It's a good question. We have done it a little bit. The way that has to happen is the section modulus of the spring has to change, and so we could vary the ID or the OD. We might be able to vary the length or the width of the spring a little bit. It's a much more heady application. Instead of doing the normal 2 or 3 billion computations that we do for for regular springs, this is going to be more complicated.
Right.
But it may be, and you can also do things like set stops for the spring, and so one portion of the spring would work up to a stop, and then another portion of the spring would work after that stop engagement.
Okay.
Okay.
All right, sounds good. All right, well, I think we're coming right up to the 3 o'clock hour here on the East Coast. So I want to take the chance here to say again, thank you to everyone who joined us here today for the webinar, and I want to remind everyone that the webinar can be found at designworldonline.com, and everybody who's registered will also get a copy of the presentation and a special white paper as well via email. A couple of other points there too. If you're still like to tweet about the webinar, you can still do so on Twitter at the hashtag DWWebinar. You can connect with Design World in various ways there through Facebook, Twitter, Google+, LinkedIn, Pinterest, and YouTube. We have a YouTube channel, just like Gary mentioned that Helical has a YouTube channel as well. And we can also carry on the discussion there at theengineeringexchange.com as well. So thanks again, everybody, and thank you, Gary, so much for your time and for your expertise today. I certainly thought it was a very, very useful and informative presentation. So thank you once again.
And thank you, Miles, and thank you all.
Okay, then everybody have a good rest of the day and a good afternoon wherever you may be. Thanks.